All right. I will begin with a word of prayer. Dear Heavenly Father, we thank you for this day. I thank you for the students, and just pray you bless this class, Lord. In your name I pray, Lord Jesus. Amen. All right, I got well, I got to get my book, right? Now, if I left my book at home, that's going to be a problem. Seriously? Oh, man. Dang it. Oh, of all the lousy. Scan. Let's see here. I think I can remember we were working on SL2C representation, and in particular we were looking at V sub D, which was the span of x to the power d and then x to the power d minus 1y all the way to x, y to the d minus 1, and then y to the d, right? So the bivariate polynomials of homogeneous degree d, which is a proper subspace of these guys. Oops. And as I recall, we were building representation from SL2C into this thing, and in particular we were building phi as a mapping from SL2C to this guy. Well, linear operators, of course, on this. That's what a representation is, right? So in order to do that, we needed to properly define what happens to E, what happens to F, and what happens to H, right? So like phi of E, phi of F, phi of H. And the definitions which we gave for those, and you'll correct me if I'm wrong, right?
Yes.
Were x partial y, was it? Or I got it backwards?
Yes, x partial y.
Okay, and then y partial x. And then x partial x minus y partial y. Is that right?
Minus y partial y.
Right. And here we're taking SL2C to be a particular we're looking at the natural representation in terms of 2 by 2 matrices, if you like. I mean, right? SL2C is it's the span of like 0, 1, 0, 0, 0, 0, 1, 0, and 1, 0, 0, minus 1. These are the traceless 2 by 2 matrices. As we saw, that was the condition that was necessary to have the exponential go to determinant 1 in the first lecture of this course. Of course, Erdmann and Wilden hasn't talked about that at all, nor do they have to. So let's see here. So E, F, and H, right? All right, so we have already last time remarked that phi of E, phi of F, and phi of H are at least, so we saw that phi of E, phi of F, phi of H were all, elements of GLVD, since it's now, I guess it's not entirely obvious to be clear. So you're like, well, you've only defined phi on E, you've only defined phi on F, you've only defined phi on H, right? VD is excuse me, you only defined, there's a couple things. Number one, like what's the general definition, like phi of v? How's that go?
Phi of v is just linear combinations, right?
Right, so like,
H is phi of ES and H's.
right, so it's understood if we had like phi of, say, C1e plus C2F plus C3H, right? Then that acts on, let's say F according to C1x partial F partial Y plus C2 Y partial F partial X plus C3, and then we've got X. I'm going to start using this notation instead, partial sub X, F minus Y partial sub Y, F, right? So that's the full-blown, that's how this phi of an arbitrary SL2C element operates on, an arbitrary F, where F is an element, of course, of VD. And of course, you can see that a couple different things, like because it's linear in the coefficients C1, C2, and C3, like linearity of phi is manifest. The fact that it's mapping from VD to VD is manifest. So this is what's the content of the book's claim that it suffices to define, the representation on the basis, right? Because then you can extend these linearly like so, and you've got a, representation that you want. Now, I think to show it's a representation, what do we need? Well, there's more to it though, right? We also saw last time that phi of h is diagonal. The matrix of phi h is diagonal with respect to the basis, which I've written here, right? We saw that last time as the last thing I wrote. So what's next in the book, Audric? I want to say it's
with the definitions, phi is a representation.
so what is it? So what does it take for phi to be a representation?
Well, we have that it's linear,
Yeah.
and now we just have to check that the Lie brackets are preserved.
Okay. So preservation of Lie brackets. So we need to see that we need. What do we need? We need that, phi of the brackets, right? So like phi of, and so here's another theorem. It suffices to show that the brackets preserved on distinct triples of the bases. Well, I guess just distinct pairs of the bases. So I need to look at I've got different things to look at, like E with F, right? And we'll start with that. Of course, there's also there's E with F, E with H, and F with H. There's those three possible pairs. If you can prove that those three pairs are preserved, then we can linearly extend those results to have preservation of the whole thing. Okay, so in order to test this, phi of that is an operator, right? So the most straightforward way is to let this act. And F was a horrible choice here, Audric. Look at this. Let me undo that. I should not write. That's the worst possible. Let's make that a V. So, but here, understand that V is a bivariate complex polynomial of degree D. I think I got them. All right, there. All right, tell no one. Okay, so let's let this act on V, right? Here's some parentheses that only I write down. See these? Okay, so what's that by definition? Let's see here. Well, you don't actually want to do that, right? What is E with F?
You can bring the brackets inside.
Yeah, but what is E with F? So this is actually phi of h acting on v, right? And phi of h was that. So we actually have x partial xv minus y partial y v, all right? On the one side, we've got that. But on the other side, we'd like to check phi of e composed with phi of f minus phi of f composed with phi of e, right? That acting on v, right? Because I'd like for these two to be equal. These two being equal is a third of what I need. Okay, so then I have phi of e acting on phi of f of v. What is phi of f of v? Well, phi of f of v is y partial xv, all right? And then I have minus phi of f, and I have to feed that phi of ev. Now, phi of ev is x partial y v, like that. And then, well, I'm glad we couldn't meet later today. I feel less horrible about not bringing my book. I blame the cousins. They were playing Fortnite with my computer this morning, and it distracted me from my usual packing routine. I blame them. I blame the children. All right, so that's x. But they're good kids. They were.
Are you sure you want to leave this B? Like,
Yeah.
I don't know what my series is going, but.
Well.
Didn't get that. Could you try again?
Sorry, that's if we're going to need to do some derivatives on B.
Well, let's just hang on here for a second. If we get stuck, I'll listen to you. And so phi of f, I mean, you might be right. Well, let's see if we can. Did he do it on a basis?
Yeah.
Yeah. Let's see if.
On arbitrary.
Yeah. So instead of doing it on v, instead he let his v be x, like x to the a, y to the b, or something, right?
Yeah.
Yeah. I think we can hack through it at this level. We'll find out soon, right? Now, the reason he may have done that is he already derived a formula on the basis for the diagonal.
Yeah.
So he's probably using that, right? But I think we can see the same just with product rule here, right? So when we do the product rule, you got yourself xy, partial y, partial xv, plus x, partial xv, minus yx, partial x, partial y, v, minus y, partial y, v. And that gives us, excuse me, x, partial x, minus y, partial y on v, which is indeedly doodly exactly phi of h acting on v, which of course is phi of ef acting on v. So the key calculation here being that the partial derivatives commute, as does multiplication of polynomials. So that's why this guy and that guy are Kaputskis. And then the other ones just give us the h. So, I mean, the book can do it on a basis if he wants. I don't think he's really gaining much doing that.
Yeah.
In this No, the book may well have deeper purposes for looking at the basis calculations that will come up later in the section, right? It's possible.
Yeah.
So, not being too critical of the book here by any means. Now, so next up we should do, let's see, which one do you want to do? E with h?
Yeah.
All right, so let's do EH. What is the commutator of EH?
Should be 2e.
So it should be 2e, all right. So 2e would be, let's see here, 2 phi of E would be x partial y v. And let's see here, but then we're supposed to be looking at phi E h and phi h with E. That changes this enough that I need to erase because the h is a little bit ugly. Do 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 do. All right. So let's see here. Phi E. So we have phi E of phi h of v. Now phi h of v, of course, was x partial x v minus y partial y v, and then minus phi h of phi E acting on v, that was x partial y v. All right. And then let's see here. That is okay. So phi E is x partial y of this. Starting to really regret using the capital X and capital Y for these calculations. You know, like lowercase x and lowercase y would make this ever so much easier to write. But this far in, I'm not giving up now. All right, so we got some product rules to contend with, like 4 of them. And so I'll just write it out, yeah? So we've got x squared partial squared yx v. Oh, and that's that per. So some of the products are 0 because like partial y, you know, partial yx is equal to 0, etc. So that's going to kill a lot of these products. So this acting on that just gives me that. This acting on that, on the other hand, gives me minus x partial y v minus xy partial squared y v. All right. Moving on to the next one, which I will do in red for some variety here. So then I get an x squared partial squared xy acting on v. And then, let's see here. And then minus x partial y acting on v. That's both from the first. And then now move on to the second term. So this on that. So this is a constant. So I really just get one term from this times that. Namely, I get minus, well, minus minus is plus. So plus yx partial squared y squared acting on v. Let's see here. We should have like 2 cancellations, right? So this guy cancels with this one, right? And the x squared term cancels with this one because, again, the partial derivative commutes. And what we're left with are the 2 remaining terms, this one and that one. What does that work out to? We got what? We got minus.
It's minus 2, or yeah, we got minus instead of plus.
Oh, okay. So minus 2 x partial y acting on v.
I think that just is a quirk of you mixing. You swap the way the
Well, this is definitely, you know, phi of,
H, phi would be,
so this,
bracket HE
but,
is 2E, not bracket EH.
I mean, this is minus 2e, right?
Yeah.
Acting on v. So we have shown that phi of EH is equal to so what you're telling me EH is actually equal to minus 2e?
Yeah, we here he has BH, BE equal to, he has bracket HE equal to 2E, not bracket EH.
Okay, so it's simple enough to fix. This is actually a minus right here, right?
Yeah.
Which minus there. And so, okay, yeah, so we should have done EH is what it boils down to. And, you know, why did I do EH instead of HE? It's just because I already had EF from the previous one, you know, so it's just the pattern. I thought it was going to be, okay, anyway, so, so we have shown the bracket of phi of E with phi of H is actually equal to phi of the bracket of E of H, right? And it's just that they're both equal to, you know, phi of minus 2e, right? If you want to, we met them in the middle at, you know, this minus 2x partial yv, which is true for all v, therefore we have the, okay. All right, so then what was left?
BH, BF.
All right. Let me see here.
You leave to the reader if you'd like to do so.
I'll at least start it. We don't need to finish it, right? But, mostly I just want to remind myself. So what's left to check is phi of, how's it go? I did what? I did EF, I did EH, now FH is what's left? So is it HF that he does?
Yeah, he does HF and then minus 2 BF.
So this is supposed to be phi of minus 2f. Is that right? And so again, we would just look at this. We would try to see that phi of h composed with phi of f minus phi of f composed with phi of h. We would check that on an arbitrary function and see that that was equal to minus 2 times phi of f, which of course would explicitly be minus 2y partial xv. Yeah, and I agree. I think we've done enough that you can see how to do that calculation. So, you say you have a scan of the book you can send to me?
Yeah.
Let me open up my other computer while you're doing that. Come on, computer. Wake up. I really just need that page or two. We won't get much further than that, right?
I'm just trying to get you actually readable things because the scanner here is like, oh, let me skew it. Maybe I should leave it at this.
Let's see here. Okay, so collecting my thoughts, what we have then is we have a representation, I suppose, of SL2C on a set of d plus 1 by d plus 1 matrices if you want to like look at it that way like we did last time. Or we could look at it in terms of operators, of course, on VD as we have here. I'm curious what he's going to do next with this. Should I erase?
He goes into here I can read you some matrix interpretation. It can be useful to know the matrices correspond to the action of E, F, and H on VD.
Okay. Okay. Yes, see here. Yeah, let me erase this. So I think we found the matrix of H last time, right? Is it that same? Is he using the same basis that we used? Well, I'll wait for your scan. If I want to let phi e act on this guy right here, I've got x partial partial y of xi yj, right? And if I want to let phi f, so see, this is see, Audric, this is where his using the calculation on the basis now pays off, because he already has these calculations done, doesn't he? Yeah. So let's see here. This one gives us x I plus 1, well, j times x to the y plus 1, y to the j minus 1. And this one gives us I x to the I minus 1, y to the j plus 1. And then you can figure what those mean for the matrices. All right, so cool. So I think this is the basic. His order of the basis is the same, right? So that with respect to the basis, we think the matrix of E, which you're looking at, is like first of all, E does to is and so it's 0, 0. So like the one bit of that D, and again, this is the D1 even matrix, right? So that context stuff, plus my D1 add. So now, right. That's the, yeah, the unique thing about these formulas. What happens? What happens when you look at like c equals to 1? What happens when you look at e equals to 1 in these representations? question.